In cost-benefit analysis, one important component is to calculate the present value of net social benefit. In the calculations, a number of mathematical techniques will be needed. In this topic, we will go through this mathematics. First, let's look at arithmetic growth versus or decline versus geometric growth or decline. Okay, let's look at this in terms of investment. Suppose I have $1 in hand. I can invest it. For example, if I deposit this $1 in bank pay me an interest rate of I. Okay, I could be 5%, 3%, whatever it is. Okay, I'm gonna have two strategies here. Strategy 1 is 1. I'm gonna say, okay, each year I'm gonna use timeline to denote. I'm using timeline to denote this cash flow. By the way, such kind of timeline is quite useful to capture the cash flow in each period conveniently. But you want to be aware of what time point that the tick on this timeline represent. Okay, let me try here. So suppose here 0, I'm using 0 to represent present time. No, that's not. So if I'm standing at 0 present time, if I take one step forward, I take one small step forward, I get into the beginning of year 1. And if I keep moving, in the end I reach end of year 1. So you want to know that the tick here, 1 here represent or denote end of the year 1. So, and this point here actually also denotes the beginning of year 1. So tick 0 also represent at the beginning of year 1. And tick 1 represent the end of year 1. At the same time, it is also the beginning of the year 2. So if you imagine that you stand at tick 1, you move forward by a small step, you start getting into the year 2. So on and so forth. So be aware about the timing of the ticks on this timeline. Alright, back to our investment here. So strategy 1, I'm going to do it this way. Say I have currently $1 in hand invested, for example, deposit to the bank. At the end of year 1, I get $1 back plus an interest rate, which is I. Then I'm going to sit, which I dollar. Okay, if I is 5%, then it's $0.05, 5 cents. And what I'm going to do now is I'm going to sit aside this. I'm going to take this $1 back. Okay, set it aside. Then in year 2, I got in year 2, this $1 from the year 1 will continue to generate interest. So I get $1 plus I dollar, 1 plus I dollar. And remember, there's another I that I set it aside in year 1. Okay, so I got $1 plus 1 plus 2 I dollar. Then I'm gonna continue the strategy to set this 2 I dollar back aside. Okay, and in year 3, I have now this 1 plus I dollar. I leave $1 in year 2. I leave $1 in the bank. So in year 3, I get 1 plus I dollar plus the 2 I dollars. I already set it aside. So I got altogether, I got 1 plus 3 I dollar back. So on and so forth until in year end, I will get 1 plus NI dollars. Okay, that's one investment strategy. Second strategy. Okay, I have again in the beginning I have $1. So in the year 1, I got 1 plus I dollar because of interest payment. Now, rather than setting this I dollar aside, I'm going to leave this I dollar in my bank account. So in the year 2, I'm going to this I dollar that I leave in the bank account will continue to generate interest payments in year 2. So in the year 2, I get 1 plus I times 1 plus I, or 1 plus I squared, 1 plus I squared. Okay, that's in year 2. In year 3, similarly, I leave the interest payment in the bank. So in year 3, I got 1 plus I raised to the power 3, so on and so forth. So in year n, I got 1 plus I raised to the power n. Okay, so now strategy 1, I got $1 in year n. For strategy 1, I invest $1. I get 1 plus NI dollar back in year n. For investment strategy 2, if I invest $1, in the end I got 1 plus I raised to the power n. And the difference between strategy 1 and strategy 2 is that in strategy 1, I set aside the interest payment each period. So in each period, this interest payment by the bank does not generate additional interest payment. So that's the difference. And we call the strategy 2 compounding. So for strategy 1, we got what we have, this arithmetic growth or decline if the interest rate is negative. And for strategy 2, we got what we call geometric growth or decline. So for the arithmetic growth, the present value, so $1 is present value, times 1 plus NI will be equal to the future value in n. Or in other words, present value will be future value divided by 1 plus NI. In contrast, for geometric growth or compounding or decline, so present value, which is $1, is equal to present value times 1 plus I raised to the power n is equal to the future value in year n, which means present value. So in our cases, usually we know the future value. We want to get the present value. So it's equal to, we want to compute the present value. It's equal to future value of n times 1 plus I raised to the power of n. So this is discounting. Okay, if it is arithmetic growth or decline, then it's kind of linear. So future value is present value times 1 plus ni. So it's linear growth or linear decline. In contrast, if it is compounding, then we have this geometric growth or decline. Present value times 1 plus I raised to the power n. Alright, and let's look at examples. Suppose revenue grows arithmetically linearly at 5% per annum from its existing level of $120. What will it be in 12 years' time? So apply this formula. Future value will be present value 120 times 1 plus n 12 years times the interest rate, the growth rate, which is roughly $192. And if we want to calculate present value for a linear growth or decline, then we get this formula. And here's an examples. If the revenue is now 150 and it had grown at 7% arithmetically for 3 periods, for 3 years, let's say, what was the revenue at time 0? So we want to calculate the present value. So it's future value divided by 1 plus n, which is 3 times the growth rate, so which 123.97. In contrast, the geometric growth or compounding, as I shown previously in previous slides. So that's the formula. Future value in year n is present value times 1 plus I raised to the power n. And to understand this formula, we can think in terms of investor PV dollars into the bank. Bank pay you an interest rate, I or 5%, and you live there for n years, and n years you get future value n dollar back. A key feature here is that every year the interest payment, you leave it in the bank, so the interest payment generate additional interest payment, and we call this compounding. Let's look at examples. Suppose costs grow at 15% per annum and are $100 now. What it will be in the 22nd years? So future value in year 2022 is present value times 1 plus interest rate raised to the power number of years. So 100 times 1.15 raised to the power of 22. So we get roughly close to $2,200. More frequently, we know the future value. We want to discount it back to present times, and this formula is the most important formulas for computing the NPVs. So present value is future value of year n plus 1 plus I raised to the power negative n. Let's look at examples. Suppose revenue has been growing at 3% per annum for 5 years, and it is now $320. So what is it at t equals 0? So we have 0, 1, 2, 3, 4, 5. So it has been growing at 3%. So I is 3% for 5 years, and it's now $320. So what it is at time 0. So what's time 0? Discounted back to time 0 x. So suppose it's x, so x times 1 plus I, 1 plus 3%, raised to the power of 5, we get a 320. Or x is equal to 320 times 1 plus 3% raised to the power of negative 5. So it's negative, be aware of it. Lovely. And plug all this number into your calculators. You can get approximately $276. Okay, one more examples. Find the present value of $3.2 million occurring in t equals 15 when the rate of discount is 12% per annum. So apply the formula. Present value is the future value, 3.2 million times 1 plus 12%, 1.12 raised to the power of negative t, negative 15. You get $628. Alright, so frequently the benefits or costs occurs as a kind of annuity. So what is an annuity? It is a sequence of equal payments at equal intervals of times. For example, weekly wages, weekly rent, or monthly dividend payments, or quarterly or annually dividend payments. There are two types, or we can think that there are two kinds of this annuity. It could be what is called general annuity, where the payments are made either more or less frequently than interest is compounded. Okay. If the compounding occurs at the same time as payments are made, we call it simple annuities. We can classify these annuities into different types. First is ordinary annuities. That's where there's a sequence of equal payments made at the end of each compounding period. For example, so this is an annuity of $10 for 5 years. So at the end of each year, there's $10 payment, $10 cash inflows for 5 years. If in contrast, this $10 occurs in the beginning of the year, so this time, present time, this is also the beginning of year 1, okay, and this is end of year 1, also beginning of year 2, okay. So if the payment occurs at the beginning of each compounding period, then we call this annuity due. You should know that in such case, the first payment is already present value, so you don't need to discount it. Sometimes annuity could be deferred annuity, which means that when payments begin after the end of the first compounding period. For example, for this annuity of 3 years, it occurs at the end of year 3. So it does not occur at the end of year 1. So this is annuity. If each period the payment continues forever, go to infinity, so $10 payment every year forever, then we call this perpetuities. Right, so we have this annuity, we have these perpetuities. Now the issue is, how can we find a formula to calculate a present value of this annuity, of these perpetuities? To do so, let's look at a particular sequence of numbers. Let's say we have a sequence of number like this: A, the first terms, then AR, I is something, and AR square, and AR 3 and ARN minus 1. Okay, so they are in terms. Okay, what is special about this sequence of numbers is that the second terms, the next term divided by the current terms is always common. So for example, AR divided by A, we get R. AR cubed divided by AR squared, we get R as well. And that's why we call this R common ratios. Alright, so what we want to do is we want to sum this up. Sum up this n terms, and let's call this Sn. Well, if n is small, then it's easy, right? We can manage it term by term. However, if n is large, how can we derive a formula for this? Okay, the trick here is that so Sn is A plus AR squared plus until AR n minus 1. What about let's say let's multiply both sides by Rsn. So A times R, so I get AR. AR times R, I get AR squared. AR squared times R, I get AR cubed. So on and so forth. So AR in minus 2 times R, I get AR in minus 1. And last terms AR in minus 1 times R, I get AR in. Sum them up. Oh, sorry, not sum them up. I'm gonna equation 1. The first equation take minus the second equation. Okay. So the left hand side Sn minus Rsn. So we can factor out Xn. So we get 1 minus Rsn. And on the right hand side, A minus, so this term cancels out with this term. 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 So terms in the middle get cancelled out. So we have A here, and these terms, because it is the first equation minus the second equation. So this term is in the second equation, we get negative. And let's pull this A, the common factor out. A 1 minus Rn. Alright, then divide both sides by 1 minus R. We get Sn is A 1 minus Rn divided with 1 minus R. Okay, so this is the formula. This is the formula of the sum of a geometric series. Okay, we called a series of this type, this shape, this pattern, a geometric series. So the sum of it is a formula. Sn is A 1 minus Rn 1 minus R. Okay, we'll apply this formula to derive present value of annuities. Okay, let's say so we have annuity. Let me see. R. Okay, let's say R. For n years, R dollars of that occurs each year for n years. And we want to calculate the present value of these annuities. So the first sense, let's discount each year back to time 0. So R discounted back, applying that discounting formula we have a moment ago. We get R times 1 plus I, which is discount rate, raised to the power negative 1. Second one, R 1 plus I, raised to the power negative 2. So on and so forth until n. That's R times 1 plus I, raised to the power negative n. And we want to sum this up. And looking at this sequence, this n terms, it's actually, you're going to find that this is a geometric series corresponding to the first term is R times 1 plus I negative 1. And the common ratio little r is the second term divided by the first term, the next term divided by the current term. So it's R 1 plus I negative 2 divided by R 1 plus I negative 1 raised to the power of negative 1. So the common ratio is 1 plus I raised to the power of negative 1. Okay, then we can apply this formula to compute the sum of this geometric series. So the present value will be equal to A, which is R 1 plus I negative 1 raised to the power of negative 1 times 1 minus common ratio is 1 plus I raised to the power of negative. Okay, the common ratio is 1 plus I raised to the power of negative 1 over 1 plus I. So minus n here divided by 1 minus 1 plus I negative 1. Okay, let's tidy this formula up. So multiply both top and bottom by 1 plus I. So R 1 plus I negative 1 times 1 plus I. One minus 1 plus I negative 1 times 1 plus I. So this cancels out with this, and we can multiply this inside. So we get R 1 minus 1 plus I raised to the power negative n. Multiply inside 1 plus I minus 1 plus I raised to the power negative 1 times 1 plus I. And this term becomes 1. Okay, so it's equal to R 1 minus 1 plus I raised to the power negative n 1 plus I minus 1. So we get the formula. I'm going to write here. Present value of this annuity is R times 1 minus 1 plus I raised to the power negative n divided by I. So here, let me erase terms. So the present value of this annuity of R dollar, the present value of this R dollars annuity for n years is PV is R times 1 minus 1 plus I raised to the power negative n I. And so we actually have a name for these terms. This term is called annuity factor. So the intuition is quite straightforward. What is the present value of these R dollars for n years? R dollar annuity for n years. It's just each period's payment times n factor. Okay, this factor depends on two things. First sense depends on the interest rate or discount rate. And the second sense depends on the number of years n, right? Now, if everything else equal, higher n, higher present values, because you have more years of payment, more periods of payments. Everything else equals higher discount rate, lower the present value, right? Because you discount each terms heavier, right? So present value of an annuity is just per period payment times n factor. Okay. So that's where this formula comes from. Let's look at these examples. Find the present value of an ordinary annuity of $250 per year for 6 years. Discount rate is 12%. So per period payment, 250 times the annuity factors, which is 1 minus 1 plus 12%, raised to the power negative 6 divided by 12%. Rough over the present value is $1,027.85. Okay. We can also calculate using the formula to calculate annuity due. Okay, so now the first payment, just know that the first payment occurs at the beginning of year 1. Okay, so now the first $200 is already present values. So that means $200 plus an ordinary annuity of 3 years. Okay, so $200 plus 200 times the annuity factor, we get $715.42. For the deferred annuities, so what we can do is, okay, this 3 years $200 occurred at the end of year 4, so we can apply the annuity formula to discount it back to 1 year before the first payment, so which is end of year 3. So then we need to further discount it back to year 0. That's what this is. Present value in year 3 times 1 plus I raised to the power negative 3. So this, we apply the annuity formula, discount it back to 1 year before the first payment. So 1 year before year 3. 1 year before year 4 is year 3. Then further discount it back. We get $409 something. So now if this annuity occurs forever, okay, so what's going to happen? So present value is per period payment times the annuity factor. So let's, if n approach infinity, if n approach infinities, then we see that this does not depend n, this does not depend n, but this depends on n, right? This is 1 plus I raised to the power negative n. So with I non-negative, with I positive, then we see that as n increase, then these terms, as n increase, then these terms approach zero, become smaller and smaller, eventually disappear. So present value of this perpetuity, so this term disappear, converge to zero, will be R time divided by I. So it's just per period payment divided by the discount rate. So we get this simple formula. And apply this formula to this example. Find present value of a flow of benefits of $175, which continues forever. So that's a perpetuity. Discount rate is 9.75%. So it's per period payment, $175 divided by the discount rate. We get close to $1,800. Right, that's the annuity and the perpetuities. Sometimes this perpetuity can grow. So, for example, so R dollar at the end of year 1, R dollar times 1 plus G, and at the end of year 2, so it grows by G. R dollar 1 plus G square, so on and so forth. So this perpetuities grows at G, rate of G, and I's discount rate. In such cases, if we want to find the present value of such kind of growing perpetuities, the first condition we need that this discount rate should be bigger than growth rate. Okay, if not, then these terms, the payment growing faster than the discount rate. In the end, when we discount it back and sum them up, we get an infinity. Okay. If given discount rate is higher than the growth rate, then the present value is equal to R, the first payment, divided by I minus G. And I won't derive this formula, but the intuition is straightforward. A constant perpetuity is the present value of this is R divided by I. Since this perpetuity is growing at G, so the factor we want to divide I is I minus G now. Okay, internal rate of returns. The IRR is a way, like NPV, of evaluating the efficiency of a project. Okay, what do we mean by IRR? Okay, in computing the present value of benefit, present value of costs, we observe that the discount rate plays an important role here. If we use different discount rate, we end up in having different NPVs. So, not surprisingly, then there might exist a particular discount rate such that the NPV, which is present value of benefits minus present value of cost, is zero. And for this particular discount rate, we call this internal rate of return. So IRR is the rate of discount which makes the present value of the benefits equal to the present value of the costs of the project. So in such cases, so if IRR is greater, if if we calculate an IRR and it is greater than the funding cost, say if the project if you calculate an IRR for a project to be 8% and you financed from the bank charge you 5%, 8% is higher than 5%, then we conclude that this project is efficient. Okay. Mathematically, IRR is a present value such that IRR is a discount rate such that present value of cost is equal to present value of benefit. So this is present value of cost, this is present value of benefit. And we know that it is high n orders, up to n orders polynomial function of R. So we want to calculate this. So essentially we want to calculate R. That means we want to solve for this high order polynomial functions. It might seem daunting. Fortunately, we have computers that can help us. For example, let's say Excel. So in Excel, there's a function IRR, which you can ask Excel to calculate the internal rate of return for you. Let's have a look. Okay, so here is a project that has the following cash flow. Net benefit here. So in the year 0, present times, so there's a net benefit of negative 20,000. Year 1, 12, year 2, negative 15,000, so on and so forth. So this project lasts for 10 years. So what is the internal rate of return of this project? Okay, it's easy. So we can just use the IRR. The inbuilt function. So input data will be B4 to B14, and is it, well, okay, let's do not guess, let's just leave it here. So it calculates for the IRR to be 47%, or let's have more digit, 46.75%. Okay, so now Excel calculate this IRR for you. The question is, how does the computer or Excel do it? Right, so essentially IRR is to solve this function 1200 times 1 plus r raised to the power negative 1 plus negative 15,000, 12,000 times 1 plus r raised to the power of negative 1 times a plus negative 15,000 times 1 plus r raised to the power negative 2, so on and so forth until 26,000 times 1 plus r raised to the power negative 10 minus 20,000. Okay. Right. What we can do is, what the computer or Excel is doing is, okay, let's guess it. Okay. So suppose if r is equal to 0.01, what's associated fr? Fr is the sum of this polynomial functions. Okay. So it calculates to be this number. If r is 0.02, it calculates to this number, and so on and so forth until 1. Okay, and let's draw a graph of this and see how we can work out the IRR. Okay, there you go. So we can see it from the graph here that this FR is we can draw this FR as a function of the discount rate R here, of discount rate R. So it's easy for us to see that the solution should be somewhere here. So that's the IRR. And how can computer set out to find it? So basically what computer can do is, okay, this case, first case will be, say, some arbitrary pick point here, evaluate FR. We find that is positive. Then another case will be, say, close to 1. Then evaluate this FR. We find that is negative. Negative. So now we know that because this FR is a continuous function of R, we know that somewhere between let's call this A and B. Somewhere between A and B, there must exist a label where FR is equal to 0, and that's where we want to find, right? Okay, so now one round we know this. Let's get into the second round of case. Okay, the next case will be, let's take the middle points between A and B, suppose here. Right, evaluate for FR. We find that it's still positive. Then we know that, okay, let's call it C. We know that the solution will be between C and B and continue to this. So now let's continue to evaluate the midpoint between C and B. Let's call this D. And we find that D is negative. So now we know that it's between C and D. And I hope now you should see that we are narrowing down towards the solution, and keep repeating this exercise. Eventually we find the solutions, the IRR we want. So this is how a computer can use this algorithm to search for the solutions. Okay, so in practice we can use this IRR functions in Excel to solve for the internal rate of returns. Let's look at examples. Assume that the same condition apply as in the previous example, excepting that the benefits continues forever. So now we have this. Okay, this project produced benefit equal to $255 per annum forever, and it requires a capital outlay of $2,000. So we want the present value of these perpetuities to be equal to $2,000. So 255 divided by R is equal to 2,000. So we get 12.75% of IRR. Okay, this is gross perpetuity. We get the present value of this. Right, the last formula we want to talk about is computing annual effective rates. In practice, you will have to decide what discount rate to use on the basis of market interest rate. And in topic 8, we will talk more about choosing an appropriate discount rate. The terms of these interest rates might not be appropriate for particular security. Interest might be paid more or less frequently than the benefits and the costs of the projects are incurred. For example, the benefits and the costs occurs at the end of every year, while interest might be given on a security which pays interest monthly. So now the point here is that, okay, the compounding period is not the same as or not the same as where the benefits and costs actually occurred. Okay, so in such cases, this is additional layer of complexity. We can address this. The easiest way to handle this issue is to convert monthly rate to an annual effective rate using this formula. Okay, then you might want to ask, where does this formula come from? Okay, let's derive this formula. So this is 1 year. Okay, so J is the nominal the interest rate per annum, nominal interest rate per annum. However, in these years, there's empiric compounding. Three in minus 1 in m. So interest are compounded at m periods. For example, m could be equal to 4, which is quarterly compounding, or m equals 12 months, monthly compounding. All right, let's say in such case, if I invest $1, at the end of first compounding period, 1, how much dollar do I have? I get $1 times 1 plus the compounding. Because the compounding, I got interest payment, right? So 1 plus an interest payment. What is the interest payment here? So this is J, that's the annual rate, nominal annual rate, discounted by M. So J divided by M, we get nominal rate for each compounding period, and raised to the power 1. Okay, raised to the power 1. That's at the end of the first compounding period. At the end of second compounding period, we get 1 times 1 plus J over M times 1 plus J over M. Or it's just times 1 plus J over N raised to the power 2. So on and so forth until end of year 1. So which is 1 times 1 plus J M raised to the power M, because they are M compounding periods. Okay, so now what is the effective interest rate? So nominally it is J, the interest rate is J, but because of compounding, because we have M compounding within this 1 years, so the effective rate is 1 times 1 plus J over M raised to the power M minus 1 divided by 1. So this is the annual effective rate. So tidy it up, we get I is equal to 1 plus J over M raised to the power M minus 1. That's where this formula comes from. Okay, let's look at examples. The benefits and costs for a project occur annually, and you are considering the interest rates on 2 securities as the discount rate. Convert the interest rates to annual effective rates. Security A, 6% nominal annual rate, compounded semi-annually. Security B, same nominal rate, 6%, but it is compounded monthly. Okay, let's apply the formula. I is equal to 1 plus 0.6% divided by 2, because there are 2 compounding periods. 2 periods. Raised to the power 2 minus 1. We get 6.09%. Similarly, for B, we get 6.17%. So you can see that the more frequently compounding is, the higher effective rate it results in. Like if it is in our example here, if it is compounded 12 times monthly, then the corresponding annual effective rate is 6.17%, higher than 6.09%, which is the rate corresponding to semi-annually compounding. All right, that's the formula. The next one, we actually already talked about this one, Fisher's equation, to convert nominal rate to real nominal interest rate, nominal discount rate to real discount rate.